Ever had to schedule a new meeting in a busy calendar and wondered where it fits? Insert interval is a Pattern Mastery 100 staple, loved by Google, Amazon, and Facebook to test your interval merging and array traversal skills. Over 30% of candidates stumble on edge cases, especially when the new event overlaps with many intervals. Master this and you'll breeze through scheduling, merging, and range questions in interviews. Let's solve insert interval using the basic approach, so you can handle any interval insertion or merging scenario step by step. You're given a list of non-overlapping intervals sorted by start time and a new interval. Insert the new interval, merging if necessary, so the output remains non-overlapping and sorted. List of intervals, each as start, end, sorted, non-overlapping new interval, start, end. List of intervals after insertion and merging. Think of adding a new meeting to a packed conference room schedule. You have to insert it in the right spot and merge if there's any overlap. Interviewers might ask, how would you efficiently handle time slot insertions in a shared calendar app? What's tricky? Need to merge if new interval overlaps with any existing. Carefully handle cases where the new interval is before, after, or in between intervals. Avoid unnecessary merges, stick to intervals that actually overlap. Loop through existing intervals. If current interval ends before the new interval starts, add it to output. If current interval starts after new interval ends, add the new interval, then the rest of the intervals, you're done. If there's overlap, merge, update the new interval start to min_cur.start, new.start, end to max_cur.end, new.end. Add any unmerged new interval at the end if needed. Let's clarify. The output must be sorted and non-overlapping. At most one merge run is needed, since input is non-overlapping and sorted. Edge cases. New interval before all others. New interval after all others. New interval overlaps multiple intervals. Initialize an empty result list. Iterate over each interval. If current ends before new starts, append current. If current starts after new ends, append new, then append the rest and return. If overlap, update new interval to merged range. After the loop, add the last new interval if not already added. Return the result. Let's walk through this solution. The main goal here is simple. Insert a new interval into a list of non-overlapping, sorted intervals and merge overlaps. If we don't resort or merge correctly, we'll get overlapping or out-of-order intervals. If we add, sort by start, then merge in one pass, everything works smoothly. Approach, insert then merge, sort time complexity. On log n starts the method that returns the updated merged list of intervals. Creates a dynamic list to hold all intervals. Copies existing intervals into the list. Adds the new interval to the list. Sorts all intervals by their start time. Prepares a list to store merged, non-overlapping intervals. Iterates through each interval in sorted order. If no intervals yet or current starts after the last merged end, there's no overlap. Adds the current interval as a new, separate block. Otherwise, intervals overlap. Updates the end of the last merged interval. Extends the end to cover the furthest end between the two. Ends overlap/non-overlap handling. Ends loop over intervals. Converts the merged list back to the required 2D array format. Ends the method. And that's how the algorithm works. The target. Efficient, simple, and elegant. Now let's verify how this solution behaves on the given test case. This represents two disjoint intervals plus a new interval that overlaps the first one. It matters because we need to merge 1, 3, and 2, 5 into a single continuous range while leaving 6, 9 alone. Short reasoning of how the algorithm processes the input and what it checks for. We copy 1, 3, 6, 9, and 2, 5 into a list, sort by start, 1, 3, we start merging. Begin with 1, 3, 2, 5, overlaps, 1, 3, so merge into 1, 5, 6, 9, doesn't overlap, 1, 5, so it's added as is. Final merged list, 1, 5, 6, 9. This matches exactly what we expect. The overlapping first interval is merged with the new interval, and the second stays unchanged. So our solution checks out, the result matches the expected behavior, and the algorithm handles this test case correctly. Let's walk through this solution. The main goal here is simple. Insert a new interval into a sorted list and merge overlaps efficiently in one pass. If we don't skip non-overlapping intervals first or merge correctly, the final timeline becomes incorrect. If we move through 3 phases, add left intervals, merge overlaps, add right intervals, everything works smoothly. Approach: one-pass merge. Time complexity: O(n). Begins the method that inserts and merges the new interval. List to store the final merged intervals. Initializes an index I and stores interval count. Adds all intervals that end before the new interval starts, no overlap. Tracks the merged intervals start and end. While intervals overlap with our new/merged interval, merge them. Expands the start if needed. Expands the end if needed. Moves to the next interval. Ends merging loop. Adds the merged interval to the result list. Adds all remaining intervals that come after the merged block. Converts list to the required 2D array format. Ends the method. And that's how the algorithm works. Efficient, simple, and elegant. Now let's verify this solution with a given test case. These intervals form a sorted timeline. The new interval, 4,8, overlaps with 3,5, 6,7, and 8,10. Understanding these overlaps is key because merging them properly determines the final correct ranges. Short reasoning. First, the algorithm adds 1,2, since it ends before 4. Then it merges 3,5, 6,7, 8,10, with 4,8. Merged becomes 3,10. Finally, 12,16 is added unchanged. Result: 1,2, 3,10, 12,16. This matches the expected behavior because the new interval correctly absorbs all overlapping ones, leaving the others untouched. So our solution checks out, the result matches the expected behavior, and the algorithm handles this test case correctly. Let's have a quick recap. We're given a sorted list of non-overlapping intervals and a new interval to insert. The goal is to place the new one correctly, merging it with any overlaps so the final list remains sorted and clean. It's all about managing order and boundaries efficiently. The challenge comes from the overlap logic. You need to handle 3 scenarios: when the new interval is before all others, after all others, or overlaps one or several intervals in the middle. The trick is merging only when necessary, not overcomplicating what's already sorted. Here's the plan. Loop through the intervals one by one. If the current interval ends before the new one starts, just add it to the result. If the current one starts after the new ends, add the new interval, then the rest, and you're done. If there's overlap, merge by taking the min start and max end, and keep going. After the loop, add the final merged interval if it hasn't been added yet. We followed this linear plan, merged overlapping intervals smoothly, and kept the final list sorted. The code ran on LeetCode successfully. No errors, no missed cases. After running the solution, every test case passed perfectly. The logic handled overlaps, gaps, and edge positions exactly as expected. All outputs matched. The key takeaway? Smart traversal beats complexity. By respecting the sorted order and merging only when needed, you can turn any scheduling or range insertion challenge into a simple, predictable one-pass solution.